In this video lesson, I want to align our current discussion of random variables with the modeling theme we committed to at the beginning of the course. To do this, I'll again look to population growth. So far, our models of this phenomenon have been deterministic. For example, we studied the differential equation model of population growth du by dt is equal to r times u. Here, u is population size, and r can be understood as the number of births that occur per individual per unit time. In this model, we're treating reproduction as a process that operates like clockwork. It has a set schedule and it sticks to it. Of course, that's not really the case. There's always some uncertainty associated with the birth of new individuals. The important question is, when must our model of population growth account for that uncertainty? In this video, we'll address this question. We'll use our newfound ability to generate pseudorandom variables to simulate population growth. Moreover, we'll simulate in a way that emphasizes the uncertainty that surrounds demographic processes like reproduction. Let's dive right in. Consider a culture of cells, maybe a population of yeast cells in a petri dish. These cells divide every so often, but we're never precisely sure when a division event will occur. There's uncertainty in that regard. Let u of t be the number of cells in the culture at time t, and let's say we start off with just one cell at time 0. We'll model the time between successive cell division events that happen anywhere in the petri dish, as a continuous random variable that's independent of the time elapsed between previous successive pairs of division events. We'll also say that the time follows an exponential distribution with rate parameter c set equal to u times a birth rate, or cell division rate, denoted r. There's a lot going on here, so let's slow things down and make sure the important details sink in. We're saying that at some point in time, there are u of t cells in our culture. Then, at some future point in time, say time t plus capital X, a cell division event will occur. At this future time, the culture will have grown in size by 1, since the division event results in a net gain of 1 cell. Our model neglects the possibility that 2 cell division events occur at exactly the same instant in time. It does allow for events to be separated by microseconds, even femtoseconds. They just can't precisely coincide. It is this time, the intervening time capital X, that we treat as our random variable. As we said, this random variable follows an exponential distribution, which means that this is its cumulative distribution function. We want to generate many independent values of capital X using a computer. Remember, we pull this off by inverting the cumulative distribution function. In this case, we start with capital F of x, replace capital F of x with y, and solve for x in terms of y. We shouldn't lose sleep over the log applied to 1 minus y here, since 1 minus y will surely be positive for the consequential bits of the calculation. Swapping the y and x leads us to the inverse function we're looking for, and we can't forget that c, the rate parameter, is equal to r times capital U. We get our exponential variables by generating uniform 0-1 variables and passing these through f inverse, as we had seen in an earlier video. Now we have our method of generating exponential variables laid out. Let's see how we use it to build a simulation model of cell culture growth. Our simulation starts with one cell at time 0. Then, at time capital X1, a cell division event occurs, giving us 2 cells in the culture. We find capital X1 by generating an exponential random variable using c set equal to 1 times r. Here, r reflects the number of cell division events that occur per individual, or per cell, per unit time, as in the deterministic model. A larger value of r means that cells tend to proliferate more quickly. The number 1 comes in because we had 1 cell back at time 0. The next cell division event occurs at time capital X2 plus capital X1, and at this time one of the 2 cells in our culture splits into 2, giving us 3 cells in the culture in total. We determine the time between events, capital X2, by generating another exponential random variable, this time with C set equal to R times 2. The number 2 here comes from the fact that at the beginning of the time interval, we had 2 cells in the culture. We continue simulating events in this way until we have a rather extensive data table. We can plot the data, and if we do, we would get something like this. You can see we have a step-like function where the rise of each step is 1, and where the run of each step is an exponentially distributed pseudo-random variable. It's difficult to extract a lesson from the cartoon plot shown here, so let's turn to a more precise plot created with a computer. Here are 2 replicate plots created with the simulation described a moment ago. In both plots, I have set R equal to 2. The simulated growth trajectory of the cell culture is shown in black and has the step-like look we expected. For comparison, I've plotted the predictions of the corresponding deterministic model in red. The predictions in red ignore the element of chance. Naturally, we want to compare the step-like trajectory in black to the smooth one in red. When we make the comparison, we definitely see some discrepancies. Red and black are making different quantitative predictions at any given point in time. What's especially noticeable on the left is that early on, nothing happens in the simulated population, whereas things chug along predictably in the deterministic red population. That said, as time goes on, the general shape of the trajectory starts to look the same. Sure, they don't overlap one another, but they do both begin to take on an exponential shape. Keeping in mind that curves are looking more and more exponential, let's now try to organize our thinking by log transforming the population size. Here are the log transformed simulation results for just one run. Of course, if we were to log transform the deterministic model, we would arrive here. Now, given the numbers we used, the deterministic model predicts log population size to grow linearly in time at rate r is equal to 2. We can see the same growth pattern reflected in the top right of the plot. There we see what looks to be a straight line of slope 2. This is better evidence that over time, as the numbers of cells grows, the simulation model behaves like the deterministic one. Early on, when numbers are small, we see that there is little to no hint of a straight line of slope 2. Here, chance events are playing a much greater role. We might now return to these plots with fresh eyes. Early on, when population numbers are small, population growth might be slow just by chance, as it is here on the left. In this case, the random early setback has a long-lasting negative impact on the population's growth trajectory, relative to expectations based on deterministic predictions. In a manner of speaking, the early setback echoes into the future. On the other hand, population growth early on might be fast just by chance, as it is here on the right. In this case, randomness boosts the population's growth trajectory beyond the predictions of a deterministic model. You can see that the early boost also sort of echoes into the future. So what have we learned? Well, we've learned that uncertainty surrounding demographic rates, like the birth rate, is an important consideration in models of population growth when the population size is small. We've also learned that this uncertainty is less important in larger populations. It seems it's more reasonable to treat the growth of larger populations as deterministic. Finally, we've seen that the effect of uncertainty can impact deterministic growth in a manner analogous to the effect exerted by altering initial population size. Let's now take a moment to recap. At the beginning of the video, we asked, when is it important to consider uncertainty in models of biological processes? This is a pretty big question, so we could only address it in part, and we did this with a case study. We focused on population growth that could otherwise be modeled using a simple differential equation. Instead of a differential equation model, though, we created a simulation by generating exponentially distributed random variables. Because it relied on random variables, or rather pseudorandom variables, our simulation reflected the kind of uncertainty not captured by the predictions of a differential equations model. By comparing the predictions of our simulation to those made by a deterministic differential equations-based model, we saw that we should especially be prepared to take randomness into account when dealing with small numbers of individuals. By the time you've mastered the ideas related to this video, you'll be able to do two key things. First, you'll be able to create a simulation of population growth when supplied with assumptions about how demographic rates, like the birth rate, can be modeled as random processes. Importantly, you'll need to be able to implement your simulation on a computer, so incorporating other skills you've been developing in the course will be an important step toward achieving this outcome. Second, you'll be able to discuss the impact of randomness on the predictions made by models of population growth. Don't forget, videos alone are not the answer to learning about mathematics and mathematical modeling. Read, explore, and interact, and I'm certain you'll conquer uncertainty.